Today we're going to talk about electronic spectroscopy. Last time we really talked about inorganic compounds, so metal centers, the splitting of the d orbitals, and today we're going to talk about just really generic molecules. I'm going to show some pictures of various azulene derivatives, but for the most part, the molecules and their electronic energy levels get so complex in organic chemistry that we just kind of punt and just draw a bunch of little lines. Okay, we don't really have good terminology for what those energy levels are, so we just call them singlet state 1, singlet state 2, singlet state 3, or triplet state 1, 2, 3. We really don't have any other better nomenclature or symbols to give to molecules. You know, in atomic spectroscopy, we had that elaborate scheme for the term symbols, right? We had triplet D, 1/2, 2/2, and all those things. But in organic chemistry, the molecules are just so complex. We just classify the whole potential energy surface as a triplet state or a singlet state. We'll start with just a diatomic picture, though, because we can still, for a diatomic, print out that potential energy. Now, we call it a potential energy surface because if you think about all of the motions of the molecule, those would be different directions in this surface, and then the y-axis on this complicated surface would be the energy. And so if you had, say, the bond stretch in this direction and a bond twist in that direction, you would have two coordinates here, and you could plot the energy as it relates to the bond stretch and the bond twist. But as you imagine, how many degrees of freedom are there in a molecule? 3 times the number of atoms, total degrees of freedom. We take away the translations and we take away the rotations, and all those vibrational modes would be different stretches, different bond angles, and those are going to be, so 3n-6 coordinates. This is a surface that can't be plotted. The most complicated potential energy surface you could plot would be 2 vibrational degrees of freedom and then the energy associated with those. But we'll still call it a surface even if it's a line like this. So in this case we have the internuclear distance for a diatomic, and we have the energy plotted versus that distance. And so even though it's a line, but it's a two-dimensional plot, I still call it a potential energy surface, a PE surface, or a PES. You'll hear all 3 of those. Okay. So don't be confused when I'm talking about this being a surface. It's just a single line of energy plotted versus internuclear distance. Now there's 2 things on this slide that I want you to take home. One is the Franck-Condon Principle. It's related to that Born-Oppenheimer approximation and the Hamiltonian. The Born-Oppenheimer approximation allowed us to separate the treatment of the nuclear positions and the electronic wave functions. So it said the electrons move so much faster, they're so much lighter than the nuclei. We can pick a position of the nuclei and then calculate the structure of the electron cloud independently. Okay. Same kind of thing happens in electronic spectroscopy. Light comes in, interacts with the lower state, and the electrons can jump to a higher state, and the nuclei haven't had a chance to move. So what does that tell you in this particular figure? It means you don't have transitions that go like this, diagonal. So from the minimum of this potential energy surface to the minimum of this potential energy surface, you have a diagonal line because the bond lengths are different. You don't have that situation because what that would require is light to come in and interact, and the nuclei slowly move to the new bond length. And light's way too fast, and the electron cloud reacts way too fast. So we don't have that type of transition. So you can put an X there. We have these vertical transitions. It goes from the lower state straight up and hits the excited state potential energy surface. And so when I talk about vertical transitions, I'm talking about vertical with respect to the nuclear coordinates. So the nuclear coordinates don't move. They don't have time to move when light comes in, and you have a vertical jump in energy to a new potential energy surface. And now that new potential energy surface may have a different structure, and that's what it's showing here on this diagram, is light is absorbed here, and then the molecule can relax, and now you have a longer bond length in the excited state than you have in the lower state. So everybody kind of follow what's going on. You understand now what a vertical transition is. It's light interacts with the wave functions of the electrons, and they jump to a higher state, and in that excited state may relax a little bit to a new structure. Okay, or it may completely dissociate. If you hit an unbound state, in other words, you've excited some bonding electrons to anti-bonding orbitals, you may have destroyed the bond order, and the molecule would just dissociate. So let's look at several potential energy surfaces on the right related to electron configurations on the left. So this is a molecular orbital diagram for oxygen, and you see how it's the lowest possible state, or the ground state for O2. It has these unpaired electrons here, and so that would give you what's called a triplet state, and this is the potential energy surface for that particular electron configuration shown here. So when the electrons are all in their ground states and they're in a ground vibrational state, then this would be the energy of the lowest energy of oxygen molecule. Now, no one asked, but you could have perhaps while we were doing molecular orbital theory, what happens if I have paired up my electrons in one of those p orbitals, right? Right, you put all the electrons as low as possible, but you still have a choice. Do I unpair the electrons and put them in separate p orbitals or pi orbitals, or do I pair them up and put them in one pi bond? Okay.
To my better knowledge, it was always you go to each one individually and then
yes.
add.
Does anybody remember the rule associated with that? There's a rule associated with that. Hund's rule. Yeah, you put them in separate orbitals first, all spin unpaired. What was that? Never mind. Okay, yeah. And so this light blue box, this electron configuration, is this particular potential energy surface. And you see it's higher in energy. And then if you moved them to the sigma antibonding orbital, it's not that much more energy to get up there, and that's this blue one, the dark blue one here. So every different electron configuration has a different potential energy surface. So when we're talking about electrons being excited to excited states and you're having a new potential energy surface, if you had a simple enough molecule, you could figure out what the configurations are for those different potential energy surfaces. Okay, and then you could even have the electrons be unpaired. So this one up here is a triplet molecule, and it's this one here. And then I've run out of space, but there's another one, a red one up here that's what we call the B state. So they are the X state. This is for at least diatomics, this holds. The X designation is for the ground electronic potential energy surface. So you see that here. This X indicates the ground electronic. And then they're labeled A, B, C, D, E, F, G, all the way up for the excited states. Now it seems like they've used lowercase letters in this particular book to indicate the ones that dissociate to ground state oxygen. So they have little a and little b, and then they have big A and big B, or capital A and capital B for the triplet versions of those energy states. And so you had a similar situation in the iodine lab. You went from the X state to the B state in visible spectroscopy. So you were going up to this particular state, but it was for iodine. And when it dissociated, it left a ground state iodine and an excited state iodine. So that's part of your lab for this week, or actually last week's lab. So let's talk now about some of the vocabulary words. The fates of the excited state. So electron has jumped up to a higher wave function. We now have an excited state molecule, and several things can happen. You can have internal conversion, so it can go from a potential energy surface to a different one of the same multiplicity. Let me go back and show you what in the oxygen where this might take place. So let's say we got that we excited this oxygen molecule to this dark blue state, and it rattled down and it got to this lower vibrational state here. But then notice how that vibrational state is the same energy as this vibrational state. And it can do internal conversion because these are the same multiplicity. And so it can just slide right on over onto this light blue state and then get a little bit lower in energy and make its way down to here. So internal conversion is swapping potential energy surfaces. And almost always happens when there's a coincidence of vibrational energy. So it's vibrating a certain amount in one potential energy surface. It gets to the end where it's supposed to turn back around and compress, and it finds itself on a new potential energy surface because the electron cloud has reacted, and it stretches a little further, and now it's on a different potential energy surface. So this internal conversion typically happens through the vibrational motion, where it can jump from one potential energy surface to another. How can it do that? Well, the electron cloud reacts so fast. So the nuclei are moving along, and it stretches out, and then the electron cloud reacts, and now the nuclei have more freedom to move, and they get onto a different potential energy surface. So that's internal conversion, moving from one potential energy surface to another with the same multiplicity. So this is the main point right here, same multiplicity. And then intersystem crossing is jumping PE surfaces, but with different multiplicity. So this is going from triplet to singlet or singlet to triplet. Dissociation, that's pretty straightforward. The molecule breaks apart. So we excite the molecule up above the ionization limit, and we knock off an electron, the molecule falls apart. That's ionization. It doesn't always have to occur with ionization. We could just hit the potential energy surface somewhere above where the vibrational manifold stops, and then it has enough energy to completely break apart. And then predissociation, we'll show a picture of this, but it's internal conversion from one potential energy surface to another, and the other one is unbound. So let's talk about the lifetimes of these different states. We excite the molecule, and then it can do two things radiatively. Moving around on the potential energy surface, a lot of times that's just changing vibrational states. But if it emits light, there's two flavors of that, if you will. There's fluorescence and phosphorescence. And fluorescence, there's no change in multiplicity. Phosphorescence, there is a change in multiplicity. And we can learn about the different excited states by doing one of these time-dependent measurements. And so we flash the light on, and we pump molecules to their excited states, and then we turn the light off, and we keep the spectrometer looking. So the source is turned off, and we're looking at light coming out of our molecule. And if the light disappears very quickly, then it's fluorescence. If the emitted light takes a long time to disappear, then it's phosphorescence. And so this equation allows us to determine it's an exponential decay, and the denominator of that exponential decay is the fluorescence or phosphorescence lifetime, and that's the lifetime of that upper state. This is the type of measurement they would do to make those glow-in-the-dark powders. So they would want powders or molecules that have a really long excited state and emit light for quite a while. So let's use these potential energy surface diagrams to talk about the different fates of the excited states. So when I talk about non-radiative relaxation, you're going to see, if you change the spectral window, you may still see radiation coming off of that molecule, but it would be in the infrared, so it would be in the form of heat. When we're dealing with non-radiative relaxation, we're typically talking about visible. So we hit the molecule with visible light, and if it relaxes all the way to the ground state and never spits out any photons, it didn't fluoresce, it didn't phosphoresce, we call that non-radiative. But there really is infrared light coming off, and infrared light is radiative, but we don't classify that in electronic spectroscopy as a radiative transition. So a lot of people get confused. They're like, if it's dropping in energy, that energy has to go somewhere, and so we just call that heat. So you excite the molecule, and it gives off heat, but we call that non-radiative because it's not in the visible region. Now, if you get intersystem crossing, notice how it, if it comes up singlet to singlet transition here, it can do non-radiative relaxation, and then there's a nice match in those vibrational energy levels, and so it can do intersystem crossing and get from a singlet state to a triplet state, and it can do more non-radiative relaxation and get lower in energy. And then it kind of gets stuck in this energy level here. What do I mean stuck? Well, that has a really long lifetime, because what has to happen for the molecule to go from a triplet state down to a singlet state emitting light. It's got to spit out a photon of light. That takes away 1 unit of angular momentum, and it's got to flip a spin. And so those are 2 events that have to happen simultaneously, and statistically, it's like rolling 2 die and getting the same number. You know, you roll 1 die, you get 1 number every time, right? But if you roll 2 die, you got to get the same number. You know, statistically, it's less probable that you'll get a spin flip and an emission at the same time. The spin flip, we call that forbidden because these lifetimes are so long. And we say it's forbidden for light to flip a spin and emit, for a molecule to flip a spin and emit light. We say that's forbidden, but it happens. Okay, so yeah, so you know, like everybody only gets 1 die, but all of a sudden you find somebody with 2, and then they have to roll and get 2 of the same number. So it's forbidden to have 2 dice, but somebody gets them somehow. I don't know. Naughty little molecules. And so then, but over here, this might be singlet to singlet or triplet to triplet. There's no change in multiplicity, and this is fluorescence here. So we'll do singlet and singlet up here. And so that, because there's no change in multiplicity, happens very quickly. Now let's talk about dissociation versus predissociation. Notice here we have this ground potential energy surface. I've drawn this little Gaussian curve because the ground vibrational state is a Gaussian. And so then you take this Gaussian shape and you hit, you know, there's molecules all over, you know, there's some molecules really stretched out, there's some molecules really compressed. The most probable distance between the molecules is the highest point on that Gaussian. So you have this distribution of molecules when light comes in. And so some of the really long molecules absorb light, and they go up to here, and you might get the 0 to 0 transition, right? V equals 0, V double prime equals 0 to V prime equals 0. That's a possibility in some molecules if they're right on top of each other. But then some of these molecules over here that are very compressed will absorb light and go way up here to the top and hit this point on that upper potential energy surface. And so now you have this molecule that's very excited. In fact, it's so excited that it dissociates. So it has this much energy and it can't get rid of all of it. So it's kind of like the ball rolls downhill and uphill and out. That's the way I picture it. Right? I've given that molecule so much potential energy, and if you were to put a marble on that potential energy surface, it would roll down through the pit and out, and it would dissociate. So anything that hits above this dissociation limit is going to give the molecule enough energy for it to break apart. And we saw that in the iodine. We saw the peaks, and they got closer and closer together, and then it just got noisy. When it got noisy, you were just dissociating iodine molecules. So you were giving those I2 molecules enough energy that they would just break apart. Now, when we were assigning those peaks in the iodine lab, we went through and assigned the quantum numbers, you know, V double prime and V prime for all of these different transitions. And it was a very well-behaved molecule. It's tedious and it was difficult, but at least you had no gaps, right? You had 20 and 19 and 18, 17, you went through and you were able to assign all of them. But occasionally you'll have a situation where the peaks disappear for a little while and then they come back. And that's when you've discovered something called predissociation. So right there, notice you've got all these nice uniform peaks, just like you have in your iodine molecule. But over here in this molecule, you've got a defined peak, and then nothing. And then the defined peaks come up again. And what that's showing you is in this region you have an intersection of 2 potential energy surfaces. And so that's predissociation. There's, where those vibrational levels are, there's no molecule really. It hits that level and then just gets dissociated. And so you don't see this nice, beautiful quantum transition. You see a continuum. Just right there where there should be 2 vibrational levels is where they intersect another potential energy surface. And so it's like you're pumping molecules out and they're breaking apart. You're not getting a nice, good, defined vibrational transition. So that's dissociation on the left, and predissociation on the right. Now both of them have this dissociation limit. You still have this up here for both, but this one on the right has this intersection with an unbound state that takes away some of the vibrational transitions that you would normally see. This stuff is also going to be most easily seen in diatomic molecules. The larger molecules are just almost too complex. So let's look at a situation where we might have some vibrational resolution. So we see the vibrational bands, and we see it in the absorption and emission curves. So this would be an experiment that you could do on the Hitachi upstairs, where you could look at the absorption characteristics of a molecule, and that's shown in green on the left, and that would be this green wave function that you see here. And you're hitting that with light, and you're hitting all of these levels up here. So you see a peak for each one of these vibrational motions. And if you were to plot all of these, the highest peak would be right above this high point here. The smaller peaks would be here and here. And so you see this green shape to the curve. That's the ground state vibrational sort of intensity, if you will, of that wave function. And those individual peaks are the Franck-Condon factors, which we've been calling them the transition dipole moment integrals. But the folks that applied that to visible spectroscopy, Franck and Condon, they got that integral named after them. So for visible spectroscopy, that transition dipole moment integral is the Franck-Condon factor, and it's the relative intensities of those transitions. And so over here, what you're really seeing is in the absorption curve, what are you noticing here? What's the spacing of these different energy levels? Is it related to the lower potential energy surface vibrational spacing, or the upper potential energy vibrational spacing? So this difference here, this is the 0 to 0 transition. And so if we're labeling this with like V double prime comma V prime, then this one right here would be what? Double prime is the lower state, so that's 0 comma 1. And this one here would be 0 comma 2. This one here, 0 comma 3. So we're changing that upper state quantum number. And so the differences in energy between all of those peaks on the left and the green curve are the upper state vibrational differences. And that's what we were assigning in the iodine lab. We had all those peaks, and we had 3 different series in overlapping, but in each individual peak, the adjacent peaks were differences in the upper vibrational states. What about emission then? This is a fluorescence spectrum. We can take our light, hit our sample, and then put the detector 90 degrees to it, so that light gets into our molecule, and then the molecule fluoresces, and that light goes out in all directions. So if we look 90 degrees, we don't see the source. We see the light coming out of the molecule. And so this emission, the fluorescence emission, is going to be coming from the ground vibrational state in the upper electronic state, and it's going to hit all of these vibrational energy levels down here. And so these here, this is the 0 to 0. What do you think this one is? It's going to be 1 comma 0 and 2 comma 0, 3 comma 0. So it's starting in that 0 vibrational state in the upper state and going down to different vibrational states in the lower electronic state. So it's a kind of a confusing situation. You've got 2 different types of excitation. You have electronic excitation and you have vibrational excitation. And so absorption tells you about the vibrations in the upper electronic state. Just look at the picture. And emission tells you about the vibrational differences in the lower electronic state. So I just think of it as, you ever see that game pachinko? It's kind of like a Japanese pinball. You know, you punch this thing and it shoots up and it bounces around through these little pins. And when it goes in these little slots, you get more balls, or you get prizes, or tickets you can exchange, kind of like our Chuck E. Cheese or Incredible Pizza. But so I think of this kind of like pachinko, right? The photon comes in and shoots the electron cloud up into some excited state, and then the molecule just goes. It's not nearly as loud as pachinko, if you've ever heard pachinko. My gosh, the glass, the balls are hitting the glass. But you shoot this molecule up into an excited state, and it's rattling down, tink, 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 and then it starts dropping, and it's hitting all of these vibrational states too. So this path, you just need to think about this path. The upward path is the absorption path. And if it's going upward, it's getting the vibrational states in the upper electronic state. And then the downward path, it filters down into this funnel and then starts dropping down and hitting the lower vibrational states in the lower excited state. Yes?
So, not quite exact, but it's kind of mirrored as it goes up. And then when it comes down, the pattern is similar.
Yes. And the only thing at lower temperature molecules, the only thing that's going to overlap in these two curves is the 0-0 transition. Okay, and that's I think that's one of the practice test questions, is what state is going to be overlapping, because you could have this transition go from right here up to the 0-0, and then you could have that same molecule, when it's compressed, come back down 0-0. But this one's not going to overlap. The 0-1 goes higher. It goes to here. So that's a longer arrow, which is a shorter wavelength. So that's this one over here. Okay, longer arrow. And then this one dropping down from 0 upstairs down to 1 here is a much shorter arrow. So the 0-1 and the 1-0 are not the same wavelength. The 0-1 is going up higher, and then the 1-0 is much shorter, and it's a longer wavelength. So the only overlap you have is the 0-0 transition. Now let's say that this equilibrium bond length is much longer in the excited state. If this whole curve shifts to the right, then you won't have the 0-0 overlap. They just will be too far away from each other. But you could estimate where it would be by calculating the gaps in those wavelengths, and then you could see where the 0-0 difference would be. You just don't have a vertical transition that connects those two. Okay. So now we're getting into molecules that are just too complex to draw, and so then we use the Jablonski diagram. So it's a sort of simplified notation for these potential energy surfaces. So here we have a fairly complex system. We have a singlet state, singlet ground state, a singlet excited state, and a triplet excited state. And so we have 3 different potential energy surfaces here. And so we're just going to take this lower singlet state, and I draw a blue box around it, and that's going to be drawn here on the Jablonski diagram. So we just draw a vertical set of a bunch of lines, and those lines represent vibrational levels. We could be accurate, I guess, and draw the vibrational spacing, but most of the time we don't. We just draw a pattern of horizontal lines. Because it can rattle down through those vibrational lines, and it can also do the rotational lines, because buried inside there are all the rotational transitions as well. You're really going to only see those in the gas phase, but even in the liquid phase or more dense phase, instead of full rotation, you still have the molecule banging into other molecules. So you have lots of quantum transitions that are buried in there. So we just don't worry about them. We just draw a bunch of horizontal lines. Yes.
One thing I've been wondering recently, is it possible for a photon to, or an energy level to skip? And it just like...
Yeah, it can. Yeah, just like an overtone absorption, you could have an overtone emission. It's just not very likely. Remember, for the particle in a box, we had a 1200 intensity of 1200, and then the intensity of the overtone was 8. So 8 versus 1200. It could do the same thing in emission. Yeah. And then up here, the singlet state, I'm going to draw with an orange box, and so that's represented over here by that S1 state. We have S0 for the ground singlet state, S1 for the excited singlet state. We just draw a box and draw a bunch of horizontal lines to represent the vibrations. And then the triplet state, we'll draw in the middle with T1, triplet state, and draw horizontal lines. Now, whether the lowest one is 0 or 1, you'll have different people do that. So the convention isn't strongly held to, in this particular case, we only have one 0 state. It's the singlet 0, and then the triplet excited state is triplet 1, and the singlet excited state is singlet 1. And so there's only one 0, and that's the ground state. But you have to read to see how they're labeling their levels. If you see this in an article, a journal article, it might be slightly different in terms of the convention for labeling 0, 1s, and 2s. And so then let's take this Jablonski diagram and take it apart of what's happening. It has everything we've talked about on it. Okay. We have blue light absorption, so high energy absorption taking us from the ground singlet state to the excited singlet state. If phosphorescence is unlikely, in other words, a spin flip and an emission, you're not going to see absorption do that. You're not going to see a spin flip and a photon be absorbed. So you can get phosphorescence, but you're not going to have the counterpart to phosphorescent absorption. So you're going to go singlet to singlet or triplet to triplet with your absorptions. You're not going to have spin flips. And so you won't see an absorption peak with this energy difference here. So this energy difference here is the singlet to triplet transition, and there won't be any absorption there. So we have light taking us to this excited singlet state, and then we think about the fate of the excited states. So it can rattle down in that singlet state and give off infrared energy and heat. And so that's non-radiative relaxation. Then you can have intersystem crossing. So it can come over here and do intersystem crossing to this triplet state. And it can rattle down, give off more infrared light, or heat up the sample or heat up the environment around it. And then you can have internal conversion. So it can jump from the singlet 1 to the singlet 0 and end up over here. And you can have that rattle all the way down, and then this one all the way down, and both of those would give off heat. So this molecule would not be a very good fluorescent molecule. So not every molecule fluoresces. And the reason this molecule would not be very good is because you have efficient paths, either with intersystem crossing or internal conversion, to get it all the way down to the ground state. So it absorbs visible light and just heats up. It doesn't fluoresce. One way to make a molecule fluorescent is to make it rigid in some way. So you fuse the benzene rings so that they can't vibrate, and you can create a fluorescent molecule. So extended ring systems are pretty fluorescent. If you have lots of rings that can twist, like biphenyl, that's not very fluorescent because it can get rid of that excited energy by vibrating. But if you lock it down a little bit, in fact, phenolphthalein is not fluorescent. But if you look at the 3 ring structures, if you would just fuse 2 of those rings together with a bridge, then you make fluorescein, which is a very fluorescent molecule. And so then you have also radiative transitions, fluorescence and phosphorescence. If the molecule gets to those lower states up here, either in the singlet or in the triplet, it can emit visible light. The way to help that out is to make the molecule a little bit more rigid. And then we have these different functional groups in a molecule that absorb light readily in the visible region. And so you think about your MO diagrams. You had non-bonding orbitals, you had pi bonds, sigma bonds, pi star, sigma star. And so we try to determine something about the molecule. What's absorbing? You can have N to pi star transitions. You can have sigma to sigma star transitions, all of those different ones. And it's just what it sounds like. You've got an electron in a non-bonding orbital, say on an oxygen, or like right here, you might have let's make this a nitric, well, let's make it a carbonyl. So we have a carbon here and an oxygen here, and those non-bonding electrons on the oxygen go to the anti-bonding orbital between that carbon and oxygen. And so this occurs typically for a carbonyl in the region of 280 nanometers. So not really a strongly colored thing. How can we get that wavelength more into the visible region? So visible region really starts at 400 nanometers. And here we have a carbonyl group that absorbs at 280 nanometers, an N to pi star transition. How can we move that into the visible region? So let's say we want to make a dye molecule or an ink for our inkjet printer. Carbonyl is useful. You can make carbonyl dyes, but a carbonyl by itself absorbs it in the UV. So how are we going to get that into the visible region? How can we lengthen that wavelength? Remember, this is the difference between two energy levels. And so right now we have the situation where we have a big difference between the energy levels. 280 nanometers. I want to get it down into the visible region. Go all the way back to the beginning of the course. We're thinking about one dimension. How did we get the energy levels to get closer together for a particle in a box? What were the three things in that energy equation that we could mess with? What? Temperature. Temperature would change the population of the energy levels, but it wouldn't change their location. Huh? Box length and what else? Mass. Okay. Mass, we're dealing with electrons. And so we'd have to try to find a new physics, to find an electron that was, but let's go with that. Let's say, would we want a heavier electron or a lighter electron? It's in the denominator, so we want a heavier electron, and that would cause the energy levels to get closer together. Okay. But what about box length? What could we do to the box length? If we shrink the box, what happens to the energy levels? The energy levels get further apart, and we want the energy levels to get closer together. So we want to extend the box. So we maybe want to put a carbonyl on an aromatic system, right? So we want to extend this electron cloud. This is right now a very small box. If we could attach this to something that had more electrons, we could lengthen that box and bring that transition into the visible region. And so that's how we make dyes and pigments and paints and so on. Here's sort of the simple functional groups on the left and their lambda max, or the height of the main peaks that they have here. But here's 4 dyes that you can make with azulene. What do you think the color of azulene is? Azul? Blue? That's how it got its name. So it's azul, azulene. And so here's a spreadsheet I wrote that takes the output from Gaussian and turns it into color. Okay, so the output from Gaussian gives you these transition wavelengths and the Franck-Condon factors, or the oscillator strengths, or the results of the transition dipole moment integral in 3 dimensions, which is really complex. Okay, and then I take those oscillator strengths and then I multiply them by these various factors here, and I use the color lab. Remember the color lab that y'all just did? To generate these curves here, these transmission curves. First, I calculate the absorption curves, convert it to transmittance, and then I use the 3 color functions and come up with the color of this molecule. And so you have the ability to make this spreadsheet. You may not believe that, but your color lab, the Gaussian work that you did, so you can model this molecule, azulene, concentrate it, which is just multiplying the absorption spectrum by a factor over here, converting those absorption spectra to transmittance, and then running through your spreadsheet and compute the sRGB values for that molecule. And so this, we see that azulene is blue. That's nice. Okay. I can put a aldehyde group on it, and it's pink. Okay. Put 2 on there, and it's red. Or I can go the other way. I can put fluorines on it and make it kind of green. And so we're just changing the box length for those electrons in azulene, and we're getting drastically different colors. And so that's how we make all our different dyes and pigments and inks, is just playing around with the box for those electrons and tuning the wavelengths to get the colors that we like. So work on the homework and the vocabulary, and I'll see you in a week. Have a happy Thanksgiving.